Welcome to the Remediation Deep Dive, your source for distilled, impactful knowledge in environmental remediation. We break down the science, the strategies, and the stories shaping our field so you can stay sharp, informed, and one step ahead. I am your host, Max Flux, and joining me today is our resident expert guide, Sandi Lomb. So let's jump right in. What if I told you that the industry standard for cleaning up contaminated groundwater might actually be making the problem vastly more dangerous?
And way more expensive.
And just to put that financial reality into perspective for you listening, the U.S. Department of Defense alone faces an estimated $31 billion in legacy cleanup costs.
Which is just a colossal amount of money.
$31 billion with a B. And when faced with that kind of scale, the industry default has, it's always been to fall back on the traditional pump and treat method.
Right. The old reliable.
Yeah, reliable maybe, in air quotes.
Yeah.
Which is exactly why we need to look closely at the Wurtsmith Air Force Base case study. We're drawing on Dr. Bernstingel's recent article in the Remediation Journal. So, for context, Wurtsmith is a Superfund site in Michigan with a massive historical AFFF plume.
Yeah, and Wurtsmith provides this really stark data set for evaluating long-term performance. So in 2015, they installed this large-scale pump and treat system to contain the PFAS migration.
Right.
And then it was significantly expanded in 2022. The capital expenditure on that, like the upfront CapEx, just to build the infrastructure, was over $6.6 million.
And when the project was greenlit, the initial 2014 models confidently predicted that this cleanup would take 30 years.
Which already sounds like a long time.
Yeah, 30 years is a career. But Dr. Bernstingel's paper points out that when you look at the first 6 years of actual extraction data, that timeline just completely shatters.
Oh, totally falls apart.
Reaching compliance for PFAS isn't going to take 30 years. Extrapolating the current curve shows it will take anywhere from 150 to 433 years.
4 centuries.
Right, which means the facility's running pumps, burning industrial electricity, and paying for hazardous waste disposal across multiple generations, just to manage a slow chemical bleed.
That is the harsh reality of it.
That shifts this from a remediation strategy to like a permanent financial hostage situation.
That's a great way to put it.
And the environmental data from a landmark paper published in Remediation Journal by Dr. Kristen Thorson and her colleagues titled Sustainability Assessment of In-situ and Ex-situ Remediation of PFAS Contaminated Groundwater. It's just staggering. I mean, over a 15-year period, the in-situ CAC barrier emitted 98% fewer greenhouse gases compared to a traditional pump and treat system.
Right, 98%. That's a massive drop.
If we're replacing a surface facility with a microscopic underground filter, what does that actually do to the bottom line? Let's dive into the CapEx versus OpEx math.
Let's do it. So, Dr. Bernstingel modeled a 30-year life cycle cost for the Wurtsmith site. The pump and treat system, factoring in its infrastructure and operation, came in at $19 million.
$19 million, okay.
Right. Designing a CAC barrier for that exact same site, intercepting the exact same contaminant flux, was calculated at $7.2 million.
Wow, $7.2 million. So that is roughly 38% of the cost of the traditional pump and treat system.
Yeah, massive savings.
And Dr. Thorson's Ramble sustainability study found almost the exact same ratio. She analyzed the total cost of ownership for a commercial airport site.
And what were the numbers there?
The colloidal activated carbon, or CAC, approach was $1.6 million, whereas the pump and treat approach was $4.1 million. So that is right at that 40% mark again.
It is incredibly consistent.
But I want to pause here and look at the front-end costs for a second. Because mobilizing direct push drilling rigs, conducting high-resolution site characterization to map the aquifer, and physically injecting thousands of gallons of liquid carbon, that isn't cheap.
No, the upfront capital is definitely significant.
Right. So if the upfront CapEx is somewhat comparable to building a pump facility, where are these multi-million-dollar savings actually coming from?
The disparity lies almost entirely in the OpEx, the operational expenditure.
The day-to-day running costs.
Exactly. A pump and treat system is a heavily mechanized industrial operation. It requires daily electricity to pull hundreds of gallons a minute from deep underground.
Right.
It requires constant mechanical maintenance. Iron bacteria fouls the screens, pumps burn out, pipes need winterizing.
It's a lot of upkeep.
And most importantly, it requires recurring, expensive changeouts of the hazardous GAC vessels, which then carry heavy disposal fees.
It's just a meter that never stops running.
Meanwhile, a CAC barrier has zero OpEx. Zero. Once the carbon is injected and the soil is coated, The system is completely passive. It is powered entirely by the natural hydraulic gradient.
Which is just the natural flow of groundwater pushing through the earth.
Yes, exactly. There are no moving parts, no electric bills, and zero hazardous waste generated on the surface.
I guess to make the financial argument bulletproof. Like, for instance, they didn't even factor in the cost of having to rip out and completely replace the mechanical pumps, piping, and infrastructure every 15 to 20 years.
Right, which you inevitably have to do.
Yeah, and when you were looking at a 150 to 400-year timeline like Wurtsmith, you would have to rebuild that surface facility multiple times over.
The actual cost disparity over a century would be astronomical. In Barnstable County, Massachusetts, a migrating plume was actively threatening a public water supply. They already had a pump and treat system in place, but it was failing to capture the full width of the plume.
So it's just leaking past the capture zone.
Yes, and worse, it was bleeding $450,000 a year just in operating costs.
$500,000 a year for a failing system.
Right, and expanding that surface system to capture the escaping mass would have required massive new infrastructure and capital.
So what did they do instead?
Instead, they installed a 617-foot CAC barrier at the toe of the plume. It rapidly dropped the PFAS levels to near or below detection limit.
If leaving it safely locked in the earth saves millions of dollars, produces zero waste, and eliminates your liability on the highway, well, maybe the best way to clean up the environment is to simply stop moving the dirt.
It demands a profound shift in perspective. The data heavily suggests that the safest place for PFAS might just be exactly where it already is, provided we can lock it down securely and permanently.
So wrapping up, this in-situ CAC treatment versus traditional pump-and-treat systems feels like a pretty significant step forward, offering a more practical, maybe sustainable option for some of these challenging PFAS sites. Well, that's all the time we have for this deep dive. We certainly hope this is giving you some valuable insights in the complex and evolving world of PFAS remediation.